Hello guys, welcome back to another New Horizon Tutoring ACT video. Again, this week we're just going to be going over some math. If you remember last week, we went over kind of some different concepts. We just started out with a review of matrices and went a little bit more in depth into one of the problems. And then we covered compound and simple interest. So just a side note, make sure that you're kind of still working on like memorizing those, especially the compound interest equation, because it is a little bit more detailed. And then we briefly went over how to use your graphing calculator to both just like enter and edit matrices. So today, like I said before last time, we're gonna work on what's called a cast diagram. And I kind of alluded to this when I mentioned it the last session, but it basically just deals kind of like with trigonometric functions and putting them onto like a coordinate plane. And the biggest factor that we're gonna deal with is the angle measurements and whether or not a certain function is going to be positive in different quadrants. So I don't know if you guys have worked with quadrants before, just in the coordinate plane. Regardless, we're going to go over them. But it ties in directly to that. Usually we don't deal with trig on the coordinate plane, but it's like the same concept of having 4 different quadrants, right? Separated by the x and the y axis. And those different quadrants are going to have different properties that apply to trigonometric functions. So this is going to be, oh shoot, I forget what page it's on, but it should be around maybe like page 5. But it's just somewhere in your math packet, kind of early in the beginning. I believe it's right after trig. So yeah, I'm just gonna go ahead, draw the cast diagram, go through some notes, and then we have a couple problems that we're gonna go through as well. Okay, so this is the kind of cast diagram just drawn out. So now I'm going to go ahead and kind of walk you through what it means, the implications that it has for doing problems with trig, stuff like that. So as I wrote up there, basically the cast diagram, when applied, is going to determine where specific trig functions are both positive and negative, depending on where the triangle is drawn within one of these 4 quadrants. So just explaining the cast diagram really quick, and then we'll kind of revisit that concept and draw a couple practice triangles and show you guys what I mean by that statement. Like, how can we determine where trig functions are positive and negative based on this cast diagram? We're going to go through that in a second, but first just describing this. So we have our 4 quadrants, right? The first one is going to be the top right hand. So that's first quadrant, second, third, fourth, just goes around in a counterclockwise circle. That's pretty simple. And then this is where the cast diagram gets its name. So we have a C labeled in the 4th quadrant, A in the 1st, S in the 2nd quadrant, T in the 3rd. And that's one way, like cast is one way to remember where certain trig functions are positive and negative. But I think it's a little bit more helpful to use this acronym. I think it's an acronym. This is how I always remember what quadrant is labeled with what letter. So it just reads, all students take calculus. And the reason that I like this one better is because it starts in the 1st quadrant and just goes all the way around, right? All students take calculus. So as long as you remember which one is the 1st quadrant and which direction to go in counterclockwise in labeling them, you'll be able to label that just just fine. So yeah, one other thing that I do want to mention that's super important is the way that this relates back to what's called the unit circle. So if you're in either pre-calc or calc right now, I know I specifically went over it in pre-calc at my school, you probably have heard of the unit circle by now, and basically it just has to do with trig and how there's like this big unit circle, and we can figure out what certain trig functions are, or like what certain trig functions evaluate out to be based on what the angle is, and it has like a bunch of different hashed marks. You don't have to know the unit circle for ACT at all, but it's the same kind of concept, right? So this line right here, that's gonna serve kind of like as our home base, right? So if we're just starting to like make a circle and go around this, we're gonna start right here. And if we're starting there, we're at 0 degrees, right? Because we haven't even drawn an angle. And then as soon as we make it to this line represents 90 degrees, which makes sense, right? Because the y and the x-axis are perpendicular, and perpendicular lines form 90-degree angles. So basically each quadrant here has 90 degrees. It just depends on what the range is. So this range from, I don't know how I want to classify that line, from the positive x-axis to the positive y-axis, that's going to be 0 to 90 degrees. Or if we're dealing with radians, which we often do with trig, right? If we're dealing with radians, then it would be from 0 to pi over 2 radians. So any kind of angle measure that falls in between 0 and 90 degrees, or 0 and pi over 2 radians, is going to lie in here. So then same exact thing as we continue on. Now we're at 90 degrees. We continue down to the negative x-axis, and now we're at 180 degrees, right? Which again makes sense because it's just the angle of a straight line, which is always going to be 180. So in this case, the range for quadrant 2 is going to be any angle that has a measure of 90 to 180 degrees, or pi over 2 to pi degrees, which even that makes sense, right? Because I believe we talked briefly about the relationship between degrees and radians. If we haven't, we can just cover it super quick. So basically, the relationship between radians and degrees is this. Pi radians is going to be equal to 180 degrees. That's kind of just a rule that you have to memorize, and then you have to be able to apply if you're working between using radians and degrees, which I'll admit you don't do too often on the ACT, which is kind of nice because it can get tricky. But as you progress in your math career, pre-calc, calc, super essential to know that and to be able to work with both units of measurement. And that's really all they are, right? Just like feet and meters are 2 units of measurement, and there's like a conversion rate between them. So they're both like measuring the same thing. Let's say I was measuring the length of this board. I could say, I don't know, that's what, like 3 feet and like 1.2 meters. I rarely don't know my measurements. But it's measuring like the same length, basically. It's just 2 different ways to say it. Same exact thing for degrees and radians. It's really just measuring a span. So since there's 180 degrees in there, it's a lot of little subsections, right? But since there's only pi, which can sometimes look like a variable, but it's actually just 3.14, there's only 3.14 divisions in a straight line. 1 radian is gonna be a lot bigger in size than 1 degree. So that'd be like, I don't know, a degree is an inch as a radian is a meter, something like that. Basically, just degrees are a lot bigger, degrees are a lot smaller than radians, but like I said before, they're measuring the same thing. So yeah, that was just kind of a side note that I wanted to make sure that we understood. And again, the range in here is going to be 90 to 180 degrees. I'm gonna go ahead and write this out actually. And something that I want to mention really quick again is, or I guess highlight the fact that whenever we're given a degree measure and we're dealing with it on the coordinate plane, we always work from the positive x-axis and then we draw it. If the angle is positive, we're gonna move in a counterclockwise direction, okay? So that's kind of where we like do this. Whenever the angle is positive, we move in a counterclockwise direction. That's just kind of a rule that you have to remember. But let's say that our angle is technically negative. That sounds weird, right? Because it sounds like we can't, like we shouldn't be able to have a negative angle, but we can. And the reason I guess that it sounds like we shouldn't be able to have a negative angle is because we think of angles like measurements, which they kind of are, right? But they're not necessarily as explicit as like other measurements. Like the example that we used with length. You can't have a negative length. Obviously, that doesn't work because it's just not physically there. But with angles, it's a little bit different, especially when we're referring to it on the coordinate plane. So let's just say that we do have a negative angle. We actually do have a problem that directly relates to a negative angle. So we'll be able to see this in action a little bit easier. But whenever we have a negative angle, let's say we want to find sine of negative 45 degrees, something like that. We still start from the positive x-axis, but this time we move in the opposite direction. Instead of moving in a positive way, counterclockwise, we move in the negative direction, which is going to be clockwise. Again, that might seem kind of counterintuitive, I guess, but if you think about it, it really doesn't. I guess I don't know why I just like automatically think clockwise should be positive, just because it seems like, it just seems like correct in my mind. But you have to remember that this all centers around the different quadrants, right? And the different labels that we have on the axes. So yeah, positive, we move in a counterclockwise direction, negative, clockwise direction. And again, that's just based on the way that the quadrants are set up and labeled. So that was kind of a tangent, I guess, but important to know. And basically, we're just gonna do the same thing, move around, kind of label our third quadrant. So again, our third quadrant spans from the negative x-axis to the negative y-axis, and that range is going to be 180 degrees to 270 degrees, or pi radians to 3 pi over 2 radians. And then same exact premise for our fourth quadrant. It's going to span from 270 degrees to 360 degrees. So that's why I labeled the positive x-axis as either 0 or 2 pi. It really depends on like whether or not you're just starting there or whether you're like finishing there. Because it's not going to be 270 to 0 degrees, right? That's not correct because we made an entire circle, which also makes sense, right? Because an entire circle is always going to have 360 degrees no matter how like big or small it is. That ties directly into like the whole concept of the unit circle. Okay. So yeah, that is just like a cast diagram in and of itself explained. I'm gonna erase a couple things just to make it a little bit more clear to see. And then we're gonna talk about how trig functions relate to this. Okay, so remember our little statement up there where it tells us that essentially the cast diagram is going to determine where trig functions are both positive and where they're negative. So now what we're gonna do, just kind of like we did before and figured out like the ranges of the angles for each individual quadrant, we're gonna talk about the qualities of each individual quadrant as it relates to whether trig functions are positive or negative. And I think the easiest way to do that is just to draw kind of like an example triangle and show you guys why the rule in that specific quadrant is the way it is. Okay, so let's say this is kind of like our example triangle, again for quadrant 1, And if you remember, I erased it just so I could draw the triangle. But quadrant 1 has a label of A. And what that stands for is that all trig functions, when written in this quadrant, are going to be positive. And the reason behind that is because if we look here, or I guess first we can label this triangle in terms of our theta, right? Kind of throwing it back to like basic trig stuff. We have our opposite, our hypotenuse, and our adjacent. So if we look here at the sign of each of those individual sides, they're all going to be positive. So since we're moving along the positive y-axis, O is going to be positive. Since we're moving along the positive x-axis, A is going to be positive as well. And since both O and A are positive, H, the hypotenuse, is also moving in a positive direction. So no matter what you divide by what, it's always going to turn out to be positive when they're in the first quadrant. Okay, so that is the explanation behind that. Again, biggest takeaway is that all trig functions drawn in the first quadrant are going to be positive. Okay, so now we're moving along to the second quadrant. Again, just trying to figure out why certain trig functions are positive and negative, and we kind of have to do like a little bit of memorizing, but the All Students Take Calculus acronym kind of helps with that a little bit. So we drew our example triangle. Now, just like last time, I'm going to go ahead and label it. So we have our opposite, adjacent, hypotenuse, and now I'm going to look and see which values are going to be positive and which values are going to be negative, centered around the whole idea of having positive and negative x and y axes. So if I look and start with adjacent here, adjacent is going to lie along the negative x axis. So adjacent is essentially going to be a negative number. Excuse me. Like I was saying, adjacent is essentially going to be a negative number. And that might seem weird because, again, it's like saying, okay, how the heck are we going to have a negative distance? But the reason is because this is on the coordinate plane, that would be a negative number, right? Let's say it's, I don't know, -2. That makes sense, right? So it's essentially just not focusing so much on like the geometry of it as it is its relation to the coordinate plane and making sure it follows the coordinate plane's rules of having both positive and negative x and y axes. So that's why the adjacent side is going to be positive, but the opposite side, the adjacent side is going to be negative, but the opposite side is still going to be positive, right? Because we're still working along that xy or positive y-axis. And then technically, actually, let me think about this. Technically, we don't have to like really worry about h in this case. But the biggest takeaway from this really, or I guess h would have to be positive if you think about it logically. The biggest takeaway in this case is that all of the sine functions are going to be positive in the second quadrant, which makes sense, right? Because sine is equal to opposite over hypotenuse. If opposite is positive and the hypotenuse is positive, positive divided by a positive, always going to get us a positive. So that's why sine is going to be positive. And then if you think about it, we also have cosecant, right? Which is really just the inverse of sine. So if sine is opposite over hypotenuse, cosecant is just hypotenuse over opposite. Since we're really not changing the sign in that, just the order that they're divided in, cosecant is also going to be positive. But if we look at either cosine or tangent, they're both going to be negative because cosine is going to be adjacent over hypotenuse. Adjacent is negative, therefore negative divided by a positive gets us a negative number. Cosine is negative in the second quadrant. Same kind of line of thinking with tangent. Tangent of theta is equal to opposite over hypotenuse. opposite is positive, or sorry, not opposite over hypotenuse, opposite over adjacent. Opposite is positive, adjacent is negative, positive divided by a negative gets us a negative number, and that is why tan functions are going to be negative in the second quadrant. Again, the only thing that is positive in this second quadrant is sine and cosine. Okay, so you're gonna see a very similar trend in the rest of these two quadrants. The trend is gonna be very similar to quadrant 2. So basically, spoiler alert, the first quadrant is the only one where all of the trig functions are gonna be positive. In all of the other 3 quadrants, only one of 3 is gonna be positive, which works out nicely because there are 3 trig functions. So that's obviously not like, I don't know, like this, the cast diagram wasn't made this way because there are 3 trig functions. It just happens to work out due to their nature. But yeah, like I said, both quadrant 3 and quadrant 4 are going to behave very similar to quadrant 2 in the way that the only trig function that is positive in quadrant 2 is sine. I bet you can probably guess which trig function is going to be positive for quadrants 3 and 4, but we're still going to go over it and kind of explain why it is the way it is. Okay, so again, working at a quadrant 3, it has the label T. So now we're just going to go ahead and label our triangle like we did last time. Okay, so now if we look at it, first things first, A is essentially the same as it was for quadrant 2. So A is still going to be negative because it's working along the negative x-axis. And in this case, O is also going to be negative, right? Because we're working along the negative y-axis. We're not moving down. In this case, H is actually going to be negative as well. H is going to be positive. And we'll kind of explain that in a second. But then moving through that, as you can see, the only trig function that's going to yield a positive result is tangent, right? Because tangent of theta is equal to opposite over our adjacent. Negative divided by negative cancels out, we're left with a positive. So that's why both tangent and cotangent are going to be positive when the triangle is drawn in the third quadrant. And then again, if we look at both sine and cosine, sine is equal to opposite over hypotenuse, negative divided by a positive. Sine is always going to be negative when the triangle is drawn in the third quadrant. Same exact thing for cosine. Cosine is equal to adjacent over hypotenuse, negative divided by a positive. Cosine is always going to be negative when it's drawn in the third quadrant. Okay, so that is the third quadrant explained. Now we're going to move on to our fourth and final quadrant. Okay, so we labeled our triangle, we drew our triangle, also labeled the sign on all of the sides. So since we're working on the positive x-axis, A is going to be positive. Since we're working on the negative y-axis, O is going to be negative and H is going to be positive. I forgot to mention this earlier, but the hypotenuse is always going to be positive. So it really just depends on whether the opposite or the adjacent are positive and negative. That is kind of going to determine it. And you won't ever have to really reason this out as long as you remember all students take calculus and you remember the basic concept behind it. I just think it's important for your general understanding to get kind of a deeper reasoning for why things are the way they are on the coordinate plane in dealing with trig functions and different angles. So yeah, this is, like I said, the fourth and final quadrant, labeled C. And if we look here, we can see that cosine is going to be the only positive trig function in this, right? Because cosine is equal to adjacent over hypotenuse. Adjacent is positive, hypotenuse is positive. Cosine and secant, because secant is cosine's inverse, right? Cosine and secant are always going to be positive when the triangle is drawn in the fourth quadrant. Then if we move on to sine, we know that sine is equal to opposite over hypotenuse. Opposite is negative, hypotenuse is positive. Negative over a positive gets us a negative number. Sine is always going to be negative when it's drawn in the fourth quadrant. Same exact thing for tangent, except tan theta is equal to negative opposite over positive adjacent. Negative over positive, again, gonna get us a negative number. Tangent is always going to be negative when the triangle is drawn in the fourth quadrant. Okay, so that was a little bit of work, but hopefully now you guys understand kind of like the rules behind this, I guess. And again, it's not super important that you're able to like reason out on the test why these things are the way they are, but I just think it really helps to see like, oh, okay, that's why only sine is positive here, because it has to do with the sine of the actual lengths of the triangle. And I just think that that kind of just contributes a better understanding of trig in general, which is always important because it's a somewhat difficult topic for some people, and it's also going to be pretty heavily tested on the ACT. Okay, so yeah, not going to spend too much more time explaining the cast diagram because I do want to get through some problems if we have time. But one thing that I do want to mention is, as I was working through the cast diagram and relating it to the triangles, I kept saying like when the triangle is drawn in the first quadrant, when the triangle is drawn in the second quadrant, etc., etc. Where you draw the triangle, because that's like a natural question that comes up, right? It's like, okay, yeah, if you draw the triangle in this quadrant, I get that, but how do I know that it's in that quadrant, right? That's an essential question. How you draw the triangle and in what triangle the quadrant is drawn in depends upon what the angle theta is. So let's say, not even like making a triangle, I just want to draw a ray that is, let's just start with, actually I'll just erase this. We're going to draw 4 different angles here. Let's start with 45 degrees. Like I said before, this positive x-axis is always going to be the basis for where we draw our rays that represent our angles, and then we can make triangles out of that. So if it's 45 degrees, I know that the first quadrant ranges from 0 to 90 degrees, right? So I know it's going to be in my first quadrant. So I'll draw roughly something like that. And then whenever I'm drawing my triangle in any quadrant, it's going to be essentially connected to the x-axis. So I didn't necessarily say this outright last time, but as I was doing it, the adjacent is always on the x-axis. It just depends on whether or not the x-axis is positive, can be negative depending on where the ray is drawn. So then that's really how you would draw a triangle in there, 45 degrees, and you're good. Okay, let's say we had an angle like 130 degrees. So again, we're starting from this kind of reference axis, positive x-axis. Now we need to draw a ray that's represented by 130 degrees. We know that our second quadrant ranges from 90 degrees to 180 degrees. Since 130 degrees falls within 90 to 180, this angle is going to be in the second quadrant. So now what we do, start from there. Obviously it's not like totally accurate, but as long as it's within that quadrant, you're good to go. And this is gonna be that 130 degrees. That's what represents it. And then again, if you wanted to draw a triangle, You just have to make sure that it's connected to the x-axis. You're never gonna like draw it this way because that's not the correct way. Because then if you think about it, in this triangle, this is theta, right? Because it's encompassing our triangle. But if I were to draw the triangle like this way, then this would be my theta. That's not what we want. So just make sure that you're drawing the triangle correctly, connecting it to the x-axis instead of the y-axis. And again, that's just an example of when you're gonna draw a triangle in the second quadrant. And the premise is essentially the same. For like, if I were to give you like 200 degrees, right? Because we know that the third quadrant ranges from 180 to 270. 200 lies within that range. So then we draw our little circle, make our ray, draw our triangle, same thing. Same exact thing if the angle is in between 270 and 360, then our ray is gonna be here. Again, that time we're just making like almost a full circle. And as you can see, all of these angle measurements, one, are positive, and two, follow basically the same exact pattern. You just have to draw the ray, make sure you figure out in what quadrant it's in. And like I've kind of exampled before, the way that you're gonna figure out what quadrant it's in is just by looking at, okay, what range does this specific angle fall into? One thing that I do want to mention is what to do if you're given a negative angle. So I kind of talked about this already, but let's say we have like negative 60 degrees, right? So we're still going to start from this little reference axis here, that positive x-axis. But like I said before, this is the direction that you move in if your angle is positive, right? Which all of the examples that we've done so far have been positive. But this is going to be the direction that you move in if your angle is negative. And again, that just depends upon, or I guess it's like determined by the way that the four quadrants are set up. So since we do have a negative angle, like I said before, we are starting from the same reference axis, but it's going to look something a little bit more like this. And again, the reason that I know that it has to be in, I'm a little wary to say this first quadrant because it's technically the fourth quadrant, is because it's in between 0 and 90. So you don't have to like go and relabel all of these angles, but at least for me, it's just like pretty common knowledge that 60 degrees is not that much, right? In the grand relative scheme where an entire circle is 360. So I know that it's gonna have to be relatively small. I know that it's gonna have to be in the first quadrant that it encounters. Even though it's technically the fourth quadrant, things are a little bit different because the angle is gonna be negative and because you have to like shift your perspective, if that makes sense. So then it would look something like that. And again, just draw a triangle like that. If the whole concept of negative angles and drawing negative angles on the coordinate plane is a little bit difficult for you to grasp, there is something you can do. So let's say, again, we're working with that example of negative 60. You can essentially make that positive and it will be the same exact measurement, the same exact triangle, if you just add 360 degrees. So then this is a little bit easier to think about in terms of like the ranges that we were doing before, right? So if I have 300 degrees and I'm thinking to myself, okay, quadrant 4 is going to contain all angles that are in between 270 and 360. 300 obviously lies within that range. So since now I'm dealing with a positive angle, again, starting from my same reference axis, now I'm moving, hit 90, 180, 270, let's call that 300. And like I said, it's going to be the same exact thing, but it might just be a little bit easier for you to like conceptualize kind of how to draw that, if that makes sense. Okay, awesome. We have like 5 minutes left. Okay, yeah, we're just gonna go through like a relatively simple problem because we don't have too much time. And then we'll go ahead and call it a day. Okay, so this question just reads, what quadrant is theta in if cosine theta is greater than 0 and cosecant theta is less than 0? So the first thing that I personally would do, since it's dealing with the CAST diagram specifically, and they don't give you like an example of the CAST diagram, is I would just super quick sketch it. So we have first, second, third, fourth. And again, if you remember our acronym, we know that all students take calculus. Okay, so first things first, I'm going to focus on this statement here where it tells us that cosine of theta is going to be greater than 0. That means that wherever theta is, wherever the triangle is in the CAST diagram, in whatever quadrant it is, cosine is going to be positive. So I know I have two options, right? My triangle could either be drawn in my first quadrant because all trig functions are going to be positive there, or it could be drawn in my fourth quadrant because cosine is positive there, and cosine theta is equal to 0, not equal to 0, greater than 0. So now that I know that, and I've kind of worked that into the problem, I'm going to go ahead and focus on this specific piece of information, which tells me that the cosecant of theta is going to be less than 0. So it's going to be negative, right? So if you think back, we know that cosecant of theta is going to be the inverse of the sine of theta, right? So now if I know that sine of theta, or technically cosine of theta is less than 0, but also sine of theta is less than 0 as well, I know that it's going to have to be my fourth quadrant, right? Because anything other than a cosine function is going to be negative in this one. Because if it was the first quadrant, sine would be positive. Cosecant would be positive. But that's not the case. It's going to be negative. So the answer would be that theta has to be in the fourth quadrant for this example. Awesome. Okay, so yeah, we have like a couple minutes left, so we're going to go ahead and call it time. I hope that all made sense. If you haven't ever seen it before, it is kind of a weird concept, especially like keeping all of the angles straight, and then you have to deal with like radians and degrees, and you have to recall all of your information about trig functions. But I would say the biggest takeaway is just to be able to draw this, because that's really going to help you. Like I said before, you don't have to like specifically be able to memorize and explain all of the mechanics behind like why certain trig functions are positive where, but you do have to memorize this, and you do have to memorize which trig functions are positive and negative where, which again, if you remember first, second, third, fourth quadrant, and all students take calculus, it's really not too bad. And then hopefully you'll be able to apply them more efficiently to problems that deal with this. Awesome. Okay, so we are going to call it a day, and we will see you guys next week. I think you guys will be seeing this one after New Year's. I'm actually going out of town, so I had to like film this before. It's not even Christmas yet when this is being filmed. So Merry late Christmas, and yeah, we will see you guys next week.